Okay, so for the first part of homework 7-5 here, we'll start with question 1, and hopefully question 1's not too bad to get through, but it's definitely a conservation of momentum problem, right? So we've got a figure skater with the initial velocity, initial moment of inertia. As the arms are pulled in, the moment of inertia should decrease, and make sure you're comfortable with why that is, right? As the skater pulls her arms in or his arms in, the mass becomes more concentrated towards the center, and that's why that moment of inertia is going down. But as soon as we realize that this is just a conservation of angular momentum, again, this problem is pretty easy. So the initial angular momentum equals the final angular momentum. Angular momentum is calculated times the moment of inertia times the angular velocity. So the initial equals the final angular momentum times, or angular moment times the angular velocity. And then it's just a matter of plugging in the measurements I know. So 2.25 times 5 radians per second equals the final moment of inertia of 1.80 times the final angular velocity, which is what we're looking for. And honestly, even if you were just reading through this question, there's really only one answer that makes sense. If you think about it, if the moment of inertia goes down, then shouldn't the angular velocity go up to compensate for that? So even as a test-taking strategy, if I just look at this right now, as soon as I realize it's conservation of momentum, option C, 6.25, is the only answer that makes any sense. And in fact, obviously, if you calculate it, it confirms that it's 6.25. But anyway, hopefully question 1, nothing too tricky. Question 2 is a pretty good example of what they can do with torque to make it slightly less straightforward. But hopefully this one, again, still not too challenging. So the biggest thing you have to realize is what the significance of that first sentence is. We've got a non-uniform 80-gram meter stick that balances when it's placed at the 51 centimeter mark, right? So what is the significance of that information? Well, the significance there is that's telling us where the center of mass is. The center of mass of the meter stick is not exactly at 50, right? So normally it'd be at the 50 centimeter mark. Instead, they're telling us the center of mass is actually, and obviously this won't be to scale, but I'll exaggerate it a little bit here, but at the 51 centimeter mark instead. That's where the force of gravity for the meter stick is acting from, right? So that's where the force of gravity for the meter stick is acting from. So then they ask, where should we place some mass, some 5-gram mass, so that the meter stick will balance at 50 centimeters? So what if instead of balancing it at 51, we want to balance it over here at 50, right? So I'm putting my pivot point, I'm putting my fulcrum, if you will, here at the 50 centimeter mark. So where do I have to place the 5-gram track, or 5-gram mass, or tack, or whatever they're calling it? So that has to be balanced out, right? Well, if I think about this, if I get a pretty good comfort with this diagram, right, I know that it's definitely going to have to be less than 50. So that actually right now tells me it's not going to be option B and it's not going to be option C. It's got to be somewhere less than 50. And as soon as I just kind of generalize this, so I'm just going to throw it over here somewhere. I don't really know exactly where it is right now, but I do know its mass. So I do know it has a force of gravity for the tack pulling down with a certain force. So as soon as we set this one up, hopefully everybody's pretty comfortable saying, hey, this is just torque. So I'm going to do the torque from the force of gravity of the tack needs to be equal and opposite to the torque from the force of gravity of the meter stick itself, right? The torque caused by the tack needs to be rotationally balancing out the torque caused by the force of gravity. And again, as soon as I set that one up, hopefully this is pretty easy. So the torque for the tack, well, it's just a 5-gram tack, so it'd be 0.005 times 9.8 times the acceleration due to gravity times the radius, which we don't know, right? The distance, which we don't know. That's what we're looking for. And then for the force of gravity of the meter stick itself, for the torque of that, it would just be the force of gravity of the meter stick, so an 80 gram, so 0.08 kilogram times 9.8. And then again, the pivotal part of this problem, if you will, I know that was a pretty good one right there, but the pivotal part is how far away is it from my axis of rotation? So in this case, it is 1 centimeter from the axis of rotation, so that is my radius, right? That's the number I use. Do not use the full 51 or it throws your measurements off. It's just how far from our axis of rotation. But anyway, as soon as I set that up, obviously it's pretty clear to see the 9.8s cancel out if I would like them to, and then I just need to solve for R. So when I solve for R, I end up getting 16, or 0.16, I guess. I get 0.16 centimeters, or meters, excuse me, which is 16 centimeters, right? So again, the thing you have to be careful about is that doesn't mean the answer is A. What that tells me is this is how far away from the pivot point that tack needs to be placed. So 16 is actually how far to the left of the pivot point I need to be located at, which means obviously then subtracting from 50, 34 centimeters is where it actually needs to be placed. So again, question 2 is a pretty good conceptual example to make sure you're comfortable with kind of the basics of torque. It throws a few twists by giving us a non-uniform beam, and it gives us some other tricks of watch out for. Make sure you know what you've actually found once you find that answer, right? Distance from the pivot point. But anyway, that's probably enough on question 2, and hopefully everybody nailed it. Question 3 here is another very good concept question, and most of you guys probably remember this from an example we saw in Physics 1 last year as well. The key concept here, though, is if you've got an object, and I'm just going to draw kind of one of these bricks off to the side. If you've got an object, then the object is going to avoid tipping. It's not going to tip as long as its center of gravity is either above the pivot point or above the contact surface. And so what I mean by that is, if this was a brick, if this was just one brick hanging off the ledge, then that brick's not going to be in danger of tipping as long as the force of gravity, as long as the center of gravity is either above the pivot point or somewhere over here to the left. Right? Obviously I could scoot that brick back and it would still be safe. But if I scoot that brick any further to the right, then it's going to be in danger of pivoting, because we'd have a torque around the edge of the ledge there, and it would then pivot and it'd fall over it'd topple over the side of the wall there. So that's a key concept. And really, then once you have that, I would just encourage you guys to kind of work your way through this and think about the options. Now, the way that I always start these problems when I can, when we're stacking either 2 bricks or 3 bricks or 4, or whatever it may be, I always kind of start my way from the top and then work my way down. And so what I mean by that is, again, looking at that top brick, if I've got 2 bricks that are placed, I know that the top one's center of gravity would have to be, to extend it as far as possible, the top one's center of gravity would have to be directly above the edge of the bottom brick, right? Which means if it's a 12 centimeter brick, I can extend it exactly halfway, so 6 centimeters either side, right? So it can extend, this top one can extend a maximum of 6 centimeters past the bottom brick. And then I know the bottom brick's center of gravity would be in its exact middle, since they're uniform bricks or blocks or whatever. So again, it's right in the middle. But the key here is I can't put the ledge underneath that, because if the ledge of the wall was underneath the center of gravity for that second brick, then the center of gravity for the entire system here, which would be somewhere between those 2 centers of mass, right? In fact, it'd be exactly midway between those 2 centers of mass. But the center of gravity for the whole system would be over the ledge and thus cause this system to topple over. So that becomes the key. I don't want to put the center of gravity of the second brick over the ledge. Instead, I want to put the center of gravity for the system, which is again going to be midway between those 2 center of gravities, over the ledge of the wall. And so all I have to think about now is where, in terms of position, is this going to be? Well, how far apart are the 2 centers of gravity? Well, if one of them has its center of gravity directly above the edge of the other one, then isn't this going to extend 6 centimeters to the middle of the other brick as well? So then if these two wooden blocks are both the same type of block, if they're both the same mass and same measurement and all that fun stuff, then isn't the center of gravity for the system going to be exactly between those 2? So in other words, it's going to split that 6 centimeters into 2 3-centimeter segments. And again, that center of gravity then would be directly above the pivot point, right? So as long as that then is directly above the pivot point, we're safe. So at this point, it's just a matter of finding out the total distance I've extended. I've got 6 centimeters from the top brick. I've got an additional 3 centimeters from the second brick, which obviously gives me a total of 9 centimeters over the ledge of the wall. This is a good question to think about. You might want to try on your own if you can, and just think about what would happen if we did 3 blocks or 4 blocks instead of just 2. Obviously, it gets a little bit more complicated, but if you take it 1 block, 1 step at a time, then you can still manage that type of problem. So I would encourage you guys, this is a very good conceptual example to think about. I would encourage you guys to think about what would happen if there were 3 or 4 blocks instead of just 2. But that's enough on this problem. Let's continue on. Okay, so example 4 here, again, hopefully one that's not too bad, and really as soon as we realize that this is a conservation of momentum problem, again, I would imagine most of us probably okay with this. I'll go ahead and write the correct answer so that way you guys can skip ahead if you feel confident with this. So 0.4 radians per second should be the final angular speed once the 2 people have stepped on. So if you got that, awesome. If not, I'll show you how I got that answer. But anyway, so it does tell us some information here, and it tells us that as each person steps on, they're doing so with negligible speed. And the biggest significance there is, as they're stepping onto the merry-go-round, we don't want there to be any outside torque, right? So if the person was like stepping on in this direction with some speed, then there'd potentially be a force, there'd be an acceleration going the opposite direction, which would then cause a torque, which would then cause a rotational change in motion, and therefore momentum would not be conserved, However, because they're stepping on, they're just barely kind of hopping onto the merry-go-round, they're not causing any great change in terms of torque. And that is one of the better circles I've probably drawn, so bask in the glory of that circle. But anyway, let's get to the actual problem. So again, because they're stepping onto the edge here without any significant torque, there's not going to cause any change. There's not going to be any type of change in the angular momentum of the system. So once again, much like my first multiple choice question, the key is my angular momentum is conserved. So my initial moment of inertia times the initial angular velocity equals my final moment of inertia times the final angular velocity. Right? So at this point, they give us the initial angular velocity, so that information is given, and we're clearly looking for the final angular speed, the final angular velocity. Right? So this is going to be the variable that I want to leave in there. So our task becomes, what about the initial moment of inertia, and what about the final moment of inertia? Well, the initial moment of inertia would just be the disk rotating by itself, right? And so if it's a uniform disk here, if it's a merry-go-round, and actually, excuse me, I was going to say we're going to use a uniform disk, but they actually gave us the moment of inertia for that merry-go-round, right? So 2,000 kilograms times meter squared. So I actually don't have to do any calculation for that. They gave me that initial moment of inertia. So then the only thing I have to think about is what happens with the final moment of inertia. Well, the final moment of inertia is going to come from three different entities, if you will, three different objects, right? We're going to have the moment of inertia of the merry-go-round itself, right? So we'll have that moment of inertia, which we already know is 2,000 kilograms, and that number does not change. But then we'll also have the moment of inertia of each of the two people. So I'll call it moment of inertia 1 for the first person and moment of inertia 2 for the second person. Now the good news with each of the two people is they're saying that they each have a 60 kilogram mass and they both step on the outer rim here of the merry-go-round. So these two numbers are actually going to end up being the same, but we do want to make sure we account for both people being on there. So again, if I want to find my final moment of inertia, then I know that my moment of inertia for the merry-go-round is 2,000. The moment of inertia for each person, because each person's mass is entirely the entire radius away from the center of rotation, I'm just going to use mr squared for each of those people. So again, I don't have to worry about any type of the special relationships or special equations. I'm just using mr squared to get there. So my final moment of inertia again would be 2,000, and then the moment of inertia for each of those people is going to be 60 kilograms times the radius, and since the radius is given to be 5, it's just 5 squared. So I have two of those measurements, and then I just can calculate my total final moment of inertia. So my total final moment of inertia, when I do that, I calculate that to be 5,000 kilograms times meter squared. So now that I've got my final moment of inertia and I already had my initial information right, I knew the initial two pieces, and then I got the final piece over here as well. So now it's just a matter of plugging everything in. So 2,000 kilograms times meter squared times the initial angular velocity of 1 radian per second equals my final moment of inertia of 5,000 kilograms meter squared times my final angular velocity, which is what I'm looking for. Obviously, as we would expect, I hope, since the moment of inertia goes up, the angular velocity should be going down, right? So anyway, when I calculate this, I get 0.4 radians per second. So that's where, again, I got my answer, 0.4 radians per second from. Anyway, question 4, again, a good conservation of momentum problem.